What if the element behind the smell of volcanoes is also the reason life exists? This is sulfur, element 16. Welcome to Atomic 118.
If you stood on the edge of, well, the very first volcanoes on Earth, your eyes would immediately water. I mean, your throat would burn, and you would probably suffocate in, like, seconds.
Oh, easily. The toxicity of the air back then was just off the chart.
Right. It was this totally hellish, violent environment. But the crazy thing is that exact toxic gas, the one that tells literally every survival instinct in your brain to run away, is the very reason you have a heartbeat right now.
It really is the ultimate paradox. What feels like the scent of death is actually the chemical signature of survival.
Which is exactly why we are doing a deep dive into it today. We are focusing on one of Earth's absolute oldest survivors.
Yeah, an element that has been here since the planet was just this molten ball of rock, silently shaping the world as we know it. Element number 16, sulfur.
Sulfur. And I want to make it clear, we're doing this deep dive because sulfur is not just some obscure, boring square on the periodic table.
Damn it.
Its story feels like a bizarre sci-fi thriller. We are going to trace it from those primordial, suffocating gas clouds straight into the DNA inside your body.
Right, and then through the literal engines of modern civilization.
Exactly. And finally out to the most violent, explosive moons in the entire solar system.
It's quite a journey, but, to really grasp the scale of what sulfur does, we have to start at the very beginning.
Back to the molten ball of rock.
Right, because billions of years ago, the Earth did not look like the peaceful blue marble we know today. It was violently active.
Just constant, massive volcanic eruptions.
Exactly. And through those massive eruptions, sulfur basically escaped from the deep core of the Earth and burst onto the surface.
Escaped is a really good word for it. It feels almost, I don't know, invasive.
It was. It mixed with the early atmosphere. It formed these complex minerals. And essentially, it laid down the entire foundation for the planet's chemistry.
So without those early sulfur eruptions, the literal ground we walk on would be unrecognizable.
Completely unrecognizable.
But, okay, here's the thing I always struggled with regarding sulfur. I always pictured it as, like, the villain of the chemical world.
Because of the smell, right?
Yes. When people hear the word sulfur, they immediately think of that rotten egg, unbearable volcanic stench. But then, you look at pure sulfur in a lab, and it doesn't fit that profile at all.
Not even a little bit. Visually speaking, pure sulfur is actually stunning.
It is.
It forms these really beautiful golden yellow crystals. And if you melt it, which is actually pretty easy to do because it has a relatively low melting point, it does something amazing.
The blue flame.
Yes, if you ignite it, it burns with this mesmerizing, almost eerie blue flame. It looks like something straight out of a fantasy novel.
It really does. It looks magical.
And the most important part, pure sulfur is completely odorless.
Wait, completely.
Totally odorless.
Right, and that is the exact detail that trips people up. If pure sulfur is this odorless, beautiful yellow crystal, why does the air around a volcano or like a natural hot spring smell so aggressively bad?
Because you aren't actually smelling pure sulfur. You're smelling its, let's call it its extroverted nature.
Okay, I like that. Extroverted how?
Well, chemically speaking, sulfur is highly reactive. It wants to bond with almost anything it encounters.
It's looking for a partner.
Exactly. So when sulfur gets heated up in nature, it reacts violently with the oxygen in the air or the hydrogen in the water.
Okay, so it's the reaction we're smelling.
Right. That famous volcano smell is actually sulfur dioxide gas, or sometimes hydrogen sulfide. It is a brilliant example of how nature hides this incredibly complex chemistry inside every breath we take.
Wow. So the element itself isn't the villain at all. It just, forms incredibly noxious partnerships.
That's a great way to put it.
It's an extreme extrovert that just hangs out with a bad crowd when it gets hot.
Exactly.
But that actually brings us to the biggest mystery of this whole deep dive.
Which is?
Well, we have established that sulfur was born in this hellish volcanic fire, right? And it naturally creates these toxic, suffocating gases. So how does something so hostile to life end up being entirely essential to living, breathing creatures? Because last time I checked, we aren't made of rock.
We aren't. But, biology doesn't exist in a vacuum. It uses whatever tools the environment provides.
Makes sense.
And if you are listening to this right now, I need you to realize that sulfur isn't just a rock you step on. It is inside you.
Like everywhere inside you.
Literally everywhere. Every single cell in your body relies on it. To put it simply, without sulfur, your biology just completely unravels.
Unravels, like literally falls apart. Because I always learned in school that carbon and oxygen were the heavy lifters for life.
Sure they are.
So where exactly does sulfur fit into the architecture of a human cell?
Well, carbon and oxygen get all the glory, but sulfur is the structural engineer.
Okay, structural engineer. Walk me through that.
In the human body, there are two incredibly critical amino acids, cysteine and methionine.
Cysteine and methionine. Okay.
And right at the core of their molecular structure is a sulfur atom. Now, amino acids are the building blocks of proteins, and proteins do, well, basically everything in your body.
Right, they repair tissues, they digest food, they build muscle.
Exactly.
Okay, let's look at the actual mechanics of that. I need a
Okay.
visual. If my body is, say, a massive skyscraper, and the proteins are the concrete and the bricks, what exactly is the sulfur doing? Is it just, like, more bricks?
No, not at all. Sulfur is the steel scaffolding hidden inside the concrete.
Oh, wow.
Okay.
Yeah.
When those amino acids link together to form a protein, the sulfur atoms literally reach out and bond with each other. They create what biologists call a disulfide bond.
A disulfide bond.
Right. And these bonds act like highly flexible steel crosslinks.
Mhm.
They physically force the protein to fold into a very specific three-dimensional shape.
And then they hold it there.
Exactly. They lock that shape into place.
And in biology, the shape of a protein completely dictates its function. So if it loses its shape, it's essentially useless.
100%. Let's take a highly visible example, right? Human hair.
Okay, hair.
Hair is made of a protein called keratin. The reason your hair has strength, elasticity, and even its specific texture is entirely due to those disulfide bonds.
Wait, really?
Yeah. If you have curly hair, it's because the sulfur atoms in your keratin are bonding in a way that physically pulls the protein strand back on itself.
So the sulfur is pulling it into a curve.
Exactly. And think about when people get a chemical perm to curl or straighten their hair. What do you think those chemicals are actually doing?
Oh my God, they are breaking the sulfur bonds.
You got it. They break those ancient sulfur bonds and force them to reform in a completely new position.
That is fascinating. We are literally manipulating volcanic chemistry just to change our hairstyle.
We really are. But, it goes way deeper than cosmetics.
Right, you mentioned our biology unraveling earlier. What happens to the internal systems if those bonds break?
Let's look at insulin.
Okay, the hormone for blood sugar.
Right. Arguably one of the most important hormones in the human body.
Mm-hmm.
Insulin is a relatively small protein, but it has to maintain a very, very precise, complex shape to fit into your cellular receptors.
Like a key fitting into a lock.
Exactly like a key in a lock.
Yeah.
And that specific vital shape is held together by exactly 3 disulfide bonds.
So just 3 sulfur bonds are keeping the whole thing functional.
Yes. If you remove the sulfur, the key loses its shape, it no longer fits the lock, and your body can literally no longer process sugar.
That is terrifying, actually. So when we say life holds itself together with sulfur, it's not some cute metaphor.
Not at all.
It is the literal chemical staple keeping our biological machinery intact.
Yes. The element we associate with fiery volcanic destruction is actually the ultimate biological glue.
Which, I mean, makes a weird kind of sense when you transition to human history.
How so?
Well, if nature used sulfur as a scaffolding tool to hold biology together, it was only a matter of time before humans figured out how to use it to hold civilization together.
Oh, absolutely. And we've been using it for a very long time.
Right, thousands of years.
Yeah, the ancient world recognized its medicinal properties way early on. Even before they understood the actual chemistry, they knew sulfur-based compounds could treat skin conditions.
And from there, human ingenuity just kind of took over, right? We mixed it with charcoal and saltpeter to invent gunpowder.
Which fundamentally and permanently
Yeah.
altered human history and warfare.
Right, and then we used it to create matches, effectively putting the power of fire right into our pockets.
That's accelerated everything.
But I want to stop and look at one specific invention, though, because to me, it perfectly mirrors what we just talked about with human biology.
Okay, what's the invention?
Rubber.
Yes.
Because natural rubber straight from a tree is essentially useless for modern applications.
Completely useless. If it gets hot, it turns into this sticky goo.
Right, and if it gets cold, it becomes super brittle and just shatters.
Yeah.
Yet today, we drive cars on rubber tires at like 80 miles an hour in the middle of the summer heat. So how did we fix the rubber?
Through a process called vulcanization, famously discovered by Charles Goodyear. And the secret ingredient, you guessed it, is once again sulfur.
Okay, break that down for me. How does it work?
Well, natural rubber is made of these long, loose polymer chains. They just kind of slide past each other.
Which is why it's a sticky goo when it's hot.
Right. But when you heat that rubber and add sulfur, the sulfur atoms form crosslinks between those loose chains.
Wait, crosslinks?
Yep.
But that is the exact same mechanism as the disulfide bonds in our proteins.
It is the exact same concept. Just like sulfur acts as the steel scaffolding in your hair and in your insulin, it acts as the steel scaffolding in industrial rubber.
That is wild.
It locks the polymer chains into a flexible, durable grid. I mean, without sulfur, you don't have tires, you don't have gaskets, you don't have the rubber seals that keep airplanes pressurized.
It is doing the identical job in a car tire that it does in human skin. I mean, that is just chemical poetry.
It really is.
But as much as rubber changed the world, the sources for this deep dive suggest that the modern era relies on sulfur for something much, much bigger.
Oh, definitely.
Apparently, the vast majority of the sulfur we mine today goes into producing one specific thing, sulfuric acid.
Yes. In the industrial world, sulfuric acid is literally known as the king of chemicals.
Okay, but why? What makes this highly corrosive, dangerous acid the quote-unquote king?
It comes down to scale and survival. Sulfuric acid is the silent backbone of the modern world.
That is a big claim.
It is. But let's look at the biggest existential challenge humanity faces today: feeding 8 billion people.
Okay.
Modern agriculture is entirely dependent on synthetic fertilizers.
Mm-hmm.
I mean, without them, crop yields would plummet and half the world would literally starve.
But plants don't absorb acid, so how does pouring millions of tons of sulfuric acid help grow, like wheat or corn?
It's all about unlocking nutrients. You see, the primary ingredient in most fertilizer is phosphorus, which we mine out of the ground as phosphate rock.
Right.
But in its natural rock form, phosphorus is completely insoluble, and plants can't eat rocks.
Right, the roots can't absorb a solid stone.
Exactly. So industrial chemists take massive, massive quantities of sulfuric acid and just pour it over the crushed phosphate rock.
And the acid dissolves it?
It does more than dissolve it. The extreme acidity breaks the chemical bonds of the rock itself, converting it into soluble phosphoric acid, which plants can easily absorb.
Wow. So the acid is basically just the hammer we use to smash the rocks open so the plants can get to the nutrients hidden inside.
That's a perfect way to visualize it. And the scale of this is just staggering. We are talking hundreds of millions of tons of sulfuric acid produced every single year just for agriculture.
Hundreds of millions of tons.
Yes, and it doesn't even stop there. It's the electrolyte fluid in the lead-acid batteries that start your car. It's essential in metal processing, in oil refining, in paper manufacturing. If you somehow remove sulfuric acid from the global supply chain, modern civilization would grind to a halt in a matter of weeks.
Which brings us to the inevitable pivot.
The dark side.
Yeah. Because we've built an entire civilization relying on this chemical scaffolding. We're using it to feed billions, we're using it to power our factories. But there is a massive catch.
There always is.
The energy required to run this massive global industrial machine comes largely from burning fossil fuels. Coal and oil.
Right.
And what exactly are fossil fuels made of?
Well, they are the compressed, fossilized remains of ancient plants and animals that lived millions of years ago.
Right, biology. And as we established earlier, all biology contains sulfur.
It does.
So when we dig up these ancient fossilized biological remains and we literally set them on fire.
We release all of that ancient stored sulfur directly into the atmosphere.
And just like the volcanic eruptions at the very beginning of Earth's history, the extreme heat of the combustion process causes the sulfur to react with oxygen,
creating our old friend, sulfur dioxide gas.
And here we are, right back to the toxic, suffocating gas from the volcano. This really is the dark side of the story, because releasing millions of tons of sulfur dioxide into the air doesn't just, create a bad smell.
No, it triggers a devastating chain reaction. The environmental cost was, for a long, long time, absolutely catastrophic.
What happens when it gets up there?
Well, when sulfur dioxide drifts up into the atmosphere, it mixes with water vapor and sunlight. It undergoes this chemical transformation and literally falls back to Earth as acid rain.
Acid rain.
Specifically, dilute sulfuric and nitric acids.
It sounds like something straight out of a dystopian movie. But this was a very real, very terrifying reality in the late 20th century.
Oh, it was a massive crisis.
Yeah.
Acid rain strips the nutrients right out of the soil, effectively killing entire forests.
Just wiping them out.
Yeah. It raises the acidity of lakes and rivers until aquatic life simply cannot survive. The water becomes toxic to fish.
And what about from a human health perspective?
It's terrible. Inhaling sulfur dioxide aggressively damages human lung tissue. It leads to severe respiratory issues like asthma, bronchitis, you name it.
So we find ourselves in this terrifying loop. We rely on sulfur to literally feed the world, but the energy we use to power that world is pumping toxic sulfur gas back into the air, poisoning the exact environment we need to survive.
The bleak picture.
It begs the question, is human progress just inherently doomed to choke on the exact same element that built it?
I mean, if we did nothing, the answer would absolutely be yes.
But we didn't do nothing.
No, we didn't. And this is where the story shifts from, environmental disaster to technological triumph.
Yeah.
We didn't just accept the doom, we engineered a solution.
Okay, I love a good engineering solution. What did we do?
Enter a technology known as flue gas desulfurization, or, much more commonly, scrubbers.
Scrubbers. I've heard that term, but I always just assumed they were like giant industrial air filters, like a physical sieve catching the bad particles before they go up the smokestack.
A lot of people think that. But a physical filter wouldn't work on a gas at that kind of industrial scale.
Oh, right, because it's a gas, not dust.
Exactly.
Yeah.
It requires, yet again, chemical judo.
Chemical judo! I love that.
So inside the smokestacks of modern coal power plants, engineers install these massive systems that spray a liquid mixture directly into the rising exhaust gas.
What's in the liquid?
Usually water mixed with crushed limestone.
Limestone. Wait, like the Rock used to build, medieval castles?
Yes, calcium carbonate. When the hot, toxic sulfur dioxide gas hits that limestone slurry, a violent chemical reaction occurs.
Okay.
The sulfur violently binds with the calcium in the rock, and it physically pulls the toxic gas completely out of the air before it ever reaches the atmosphere.
That is brilliant. Just brilliant. But wait, basic physics says matter cannot be created or destroyed, right?
Correct.
So if we pull millions of tons of sulfur gas out of the air inside a smokestack, it has to go somewhere. What exactly does that chemical reaction create at the bottom of the stack?
It creates solid calcium sulfate, but you probably know it by its much more common name, synthetic gypsum.
Wait, gypsum, as in the stuff used to make drywall.
Exactly. The core construction material used to build the interior walls of almost every single modern house and apartment building.
Are you serious?
I am. By using scrubbers, we literally capture a toxic gas that causes acid rain, we force it through a chemical reaction, and we turn it into the literal walls of our homes.
Taking poison from the sky and turning it into a living room? That is unbelievable.
It really is. It's a perfect example of how technology can actually find a balance between massive industrial progress and protecting the natural world.
But it's a constant effort, right?
Oh, absolutely. It is a constant active effort. We have to continually use our understanding of chemistry to clean up the messes that our industrial ambitions create.
Wow. Okay, so we've gone from the fiery core of the Earth, deep into the microscopic folding of human DNA, out to the massive scale of industrial agriculture, and up into the smokestacks fighting acid rain.
You've covered a lot of ground.
We have. But we actually cannot end this deep dive on Earth.
No, we can't.
Because the story of element 16 is a universal one.
It really is.
Yeah.
When we send probes and rovers out into the cosmos, we find sulfur waiting for us almost everywhere we look.
Like where?
Well, Mars is completely covered in sulfur-rich minerals. And scientists study them really closely because they act as chemical fingerprints. They basically prove that ancient, watery environments once existed there.
Okay, so it's a clue to Mars's past.
Right. And we've also detected heavy sulfur signatures on the frozen crust of Europa, which is one of Jupiter's icy moons.
But if we are talking about sulfur in space, we really have to talk about the absolute star of the show.
Oh, I know where you're going with this.
The most visually cinematic location in our entire solar system, another one of Jupiter's moons, Io.
Io is mind-blowing.
If you think Earth's early volcanoes were violent, Io makes them look like, I don't know, cozy little campfires.
It really does. You see, Io is caught in this brutal gravitational tug-of-war between Jupiter and a few of the other really large moons.
Just constantly getting squeezed.
Right, constantly squeezed. And this massive gravitational friction literally heats the moon from the inside out.
Right.
It makes it the most volcanically active body in the entire solar system.
Which is saying something.
It's covered in hundreds of massive, continuously erupting volcanoes.
And those eruptions, the stuff spewing out of them, is pure sulfur.
Yep.
I mean, if you look at high-resolution images of Io taken from space probes, it doesn't look like a dead, gray, cratered rock like our moon.
No, not at all.
It looks like a vibrant, chaotic painting. It's completely covered in these patches of brilliant yellow, deep blood red, bright orange, and stark black.
And every single one of those colors is just sulfur in a different physical state or at a different temperature.
That is just wild.
The volcanic activity is so relentless that Io is constantly turning itself inside out. It is literally repainting its entire surface with fresh layers of molten sulfur compounds every single day.
It is a cosmic canvas painted entirely with fire in element 16. It's awe-inspiring, really, because it proves that fundamental chemistry is the exact same everywhere in the universe.
It is.
The exact same element that is actively paving the surface of a moon hundreds of millions of miles away in space is currently floating through your bloodstream, keeping your insulin intact so you don't die.
That is the universal thread. The laws of chemistry do not change just because the zip code does.
What an unbelievable journey. I mean, from the hellish, primitive volcanoes of early Earth, acting as the foundational building block for our planet,
Right.
then migrating into biology, acting as the invisible steel scaffolding that gives structure to our hair, our skin, and the hormones that keep us alive.
And then human beings taking that exact same mechanism of cross-linking to vulcanize rubber, building the tires that literally drive our civilization.
We weaponized it in acid to feed billions, accidentally poisoned our own skies, and then engineered chemical scrubbers to turn that exact same poison into drywall.
It's incredible.
And as we look up at the night sky, we see that same yellow crystal painting the moons of Jupiter. Sulfur really is the silent, often totally misunderstood architect of matter.
It is. And, if you will allow me, I want to leave you with one final kind of provocative thought regarding that architecture.
Oh, please do.
We established earlier that sulfur is the essential bridge between violent, lifeless geology like molten volcanoes and delicate, complex biology like the folding of proteins.
Right. Geology provides the raw sulfur, and biology uses it to build life.
Exactly. So
Sure.
consider the modern search for extraterrestrial life.
Okay.
Astronomers right now are scanning thousands of distant exoplanets looking for biosignatures. But what if the key to finding alien life isn't looking for oxygen or water right away?
What else would we look for?
What if the absolute best compass we have is looking for that exact same, quote-unquote, terrible volcanic smell? Think about it. If we detect an exoplanet with massive amounts of sulfur dioxide cycling through its atmosphere, it tells us the planet is geologically active enough to provide the chemical scaffolding necessary for life.
Wow. So the very smell that makes us gag and run away, wait, that could end up being the beacon that proves we aren't alone in the universe.
Exactly. It could be the scent of alien life.
That is a thought that is definitely going to linger. I mean, wow. Well, the story of sulfur stops here for today, but our journey across the periodic table is just gaining momentum.
Oh, we are just getting started.
Next time, we are diving into element 17, chlorine.
Ooh, that is a wild one.
And I promise you, it is a completely different, incredibly dark, yet equally vital chapter in the story of matter. You absolutely do not want to miss it.
If you enjoyed exploring the amazing world of elements with us, follow Atomic 118 and join us as we uncover the story behind every element of the periodic table. See you in the next episode.